So I'll first start with the kinetic molecular theory of gases. And this is, I'll say, i.e. the description of an ideal gas. Okay, so this is the description of an ideal gas. Number one, molecules are so small, their volume is negligible compared to volume between molecules. So what does all of that mean? So I'm going to draw once again another balloon here, okay? And when I talk about the volume inside this balloon, we actually didn't consider the volume of the molecules themselves. We only talked about the volume of that balloon. Well, as it turns out, there's little molecules in here, right? Each of these little dots. And they actually occupy volume, okay? But when we use the ideal gas law, we didn't use that. So in this description of an ideal gas, we say the molecules are so small their volume is negligible. Well, as it turns out, there's conditions where that is not true. And that's what we call a real gas. So we will talk about when this is not true. But when we're assuming that a gas behaves ideally, then this point number one is true. Okay, number two, molecules are in constant random motion. Pressure is a result of collisions with the wall. Okay, so this is not only true with ideal gas law, but this is also true with real gases. Okay, so I'm going to make a column here. We'll say real gases, ideal gases. Okay, so that means that the pressure that we measure in this balloon is actually a result of all of these little molecules colliding with the wall. Okay, now that's true for ideal gases, that's true for real gases. But what's also true, what is also going on in real gases is that those molecules can actually collide with each other. So let's go to point number three. Molecules have no interaction with each other. That's true with ideal gases, but not so much with real gases, okay? So molecules, for real gases, they do interact with each other. And those interactions create more collisions, okay? But in the ideal gas approximation, molecules have no interaction with each other. Okay, number four, this is true for both ideal gases and for real gases. The average, and I'm going to underscore, box, highlight, average kinetic energy is directly proportional to temperature. So in other words, as you increase the temperature of a gas, you increase its kinetic energy. Well, kinetic energy gives us the energy of motion. So when all these gases are moving around, colliding all over the place, okay, the hotter they are, the more crazy they're moving around, the more kinetic energy they have. This was what we saw as the case in Charles' law with volume and temperature, right? As those gases get hotter, they push the balloon out. As they get colder, they condense, okay? So let's get into this a little bit more, all right? So here's kind of the idea behind this pressure and collisions and so on. So here we have the wall, and the wall would be like the, the outside of our container, okay? When you have a low pressure sample, there's very little interaction of this molecule interacting with the wall. When we have a high pressure sample, not only can all these molecules collide with the wall, but they can all collide with each other, okay? And so when we start to think about all these kinetic molecular theory things I talked about, like, the molecules not having any volume or the molecules not having any interaction with each other, then as it turns out, this, and I'm going to put it in quotes, low and high, because we don't really have a baseline for what that means yet. Small or big. Well, what's in the middle, right? What number is in the middle, okay? So well, as it turns out, this is kind of a picture of an ideal gas, right? Low pressure, as it turns out, is very ideal, okay? High pressure is very non-ideal, or reality. Okay? Doesn't have to mean that when you're in a low pressure environment, you're not in reality. It just means when you're in low pressure, gases are going to behave ideally. When you're in a high pressure sample, gases are going to behave non-ideally because of all these collisions and also because of the volume that we're not accounting for from these molecules themselves. Okay?